financial diversification and portfolios. The principle of diversification says that you can reduce your risk by holding small investments in multiple assets compared to putting all of your money into one asset. That is, you shouldn't put all of your eggs in one basket. The math of diversification follows from equation 2.46. Suppose you divide $1 equally among n assets. Let big Y sub 1 represents the payout in 1 year of $1 invested in the ith asset. Because you invested 1 over n dollars in each asset, the actual payoff of your portfolio after 1 year is open big Y sub 1 plus big Y sub 2 through big Y sub n, close over n equals big Y bar. To keep things simple, suppose that each asset has the same expected payout, mu sub big Y, the same variance, sigma squared, and the same positive correlation rho across assets, so that covariance of big Y sub I and big Y sub j equals rho sigma squared. Then the expected payout is the expectation of big Y bar equals mu sub big Y. And for large N, the variance of the portfolio payout is a variance of big Y bar equals rho sigma squared. Exercise 2.26. Putting all of your money into one asset or spreading it equally across all n assets has the same expected payout, but diversifying reduces the variance from sigma squared to rho sigma squared. The math of diversification has led to financial products such as stock mutual funds, in which the fund holds many stocks and an individual owns a share of the fund, thereby owning a small amount of many stocks. But diversification has its limits. For many assets, payouts are positively correlated, so variance of big Y bar remains positive even if n is large. In the case of stocks, risk is reduced by holding a portfolio, but that portfolio remains subject to unpredictable fluctuations of the overall stock market. Back to the text. In summary, if big Y sub 1 through big Y sub n are independently and identically distributed, the mean, the variance, and the standard deviation of big Y bar are the expectation of big Y bar equals mu sub big Y equation 2.47, variance of big Y bar equals sigma sub big Y bar squared equals sigma sub big Y squared over n, equation 2.48, and standard deviation of big Y bar equals sigma sub big Y bar equals sigma sub big Y over the square root of n, equation 2.49. These results hold whatever the distribution of big Y is. That is, the distribution of big Y does not need to take on a specific form, such as the normal distribution, for equations 2.47 through 2.49 to hold. The notation sigma sub big Y bar squared denotes the variance of the sampling distribution of the sample average big Y bar. In contrast, sigma sub big Y squared is the variance of each individual big Y sub I, that is, the variance of the population distribution from which the observation is drawn. Similarly, sigma sub big Y bar denotes the standard deviation of the sampling distribution of big Y bar.